the greatest success story in space travel has a name, and it's not James Webb. No, because the two Voyager probes have actually been flying through the vast expanses of space for 47 years now, giving us ever new insights into unknown cosmic worlds as humanity's most remote outposts. The identical sister probes have now even ventured into interstellar space, and they have shown us that the regions at the edge of the solar system are much stranger than previously thought. But how can the strange differences that the probes have recorded at the threshold of our home system be explained? And what about the gigantic, mysterious wrinkled structures lurking in the heliosphere? Looking back, 1977 seems almost like something from another world. Indeed, it was the year that Jimmy Carter became President of the United States, the last time the guillotine was used for an execution in France, and the cult film Rocky won 3 Oscars. But as is well known, something else happened in 1977 that still spans the arc to the present day, the launch of the two NASA space probes Voyager 1 and 2. The first probe to bid farewell to Earth was Voyager 2. It set out on August 20, 1977 to explore the previously largely unexplored areas of our outer planetary system. Voyager 1 followed 16 days later on a different trajectory. But at the time, no one could have known that this was the starting signal for by far the longest-lasting mission in modern space travel. At the beginning of the program, it had not been planned at all that Voyager 1 and 2 would one day have an incredible distance of 24.63 and 20.59 billion kilometers respectively between them and the Sun. Because, as already mentioned, the probes had actually only set out to gather new insights into the outer planets of the solar system. Indeed, the endeavor was not even under a lucky star at first. Communication with Voyager 2 caused problems from the very beginning. Fortunately, however, NASA experts were able to quickly resolve the complications and finally pave the way for the record-breaking mission, setting out for unknown worlds. Today, we live in a time in which the James Webb Telescope presents the outer representatives of our planetary system to us in an unprecedented level of detail. But almost 50 years ago, the situation was completely different. When Voyager 1 and 2 set out into space, our knowledge of the distant planetary worlds was, to say the least, limited. And so it came to pass that the first items on the research checklist concerned the Jupiter and Saturn systems, and that the terrestrial experts were soon enriched with many extensive measurements and numerous images. In the process, our understanding of the gigantic gas giant and the iconic ring planet was taken to a whole new level. While it was then time for Voyager 1 to set a course for interstellar space, the further journey of Voyager 2 had a few more exciting stopovers in store. A corrective maneuver in the spring of 1981 and later, the probe was on its way to Uranus, which it reached on January 24, 1986. And just to be clear, by this point, Voyager 2 had already exceeded its originally predicted lifespan by a factor of 2. However, since the spacecraft apparently didn't care much about any earthly predictions, it not only took a close look at Uranus but also discovered 10 previously unknown moons of the remote ice giant in the same breath. The next stop was to be Neptune, and this time, it was supposed to be the final chapter of the research mission. There were simply no plans to fly by any other destinations, which is why the more than 9,000 photos taken by Voyager 2 of the outermost planet in the solar system were, at the time, tantamount to a pictorial farewell. However, the probe did not just diligently take pictures of its surroundings, but also added 9 previously unknown satellites to the star maps. Triton, the largest of Neptune's moons and already known at that time, was to be examined in detail. In the course of this, Voyager 2 provided the insight that its diameter is not 5,000 kilometers as previously assumed, but only 2,760 kilometers. Furthermore, it found that the brownish-white surface of the satellite had surprisingly few impact sites and that numerous geysers are dormant here, regularly spitting liquid nitrogen onto their surroundings. To reach the next milestone of the Voyager program, we have to turn back the clock a little to the year 2012. This is not surprising, since this distant area, which the mighty arm of the Sun can no longer reach, is not exactly around the corner. This distant cosmic realm is filled with interstellar medium, the most important components of which include dust and ionized atomic and molecular gas. While these components together form the interstellar matter, the interstellar medium is completed by the galactic magnetic field and electromagnetic radiation. Voyager 1 passed the boundary of the solar system in 2012, its sister probe followed in November 2018. Just as they once did on our planetary doorstep, the spacecraft are taking unprecedented measurements here. However, since the probes are not traveling in the same region, experts have had the exciting opportunity to study the interstellar medium at two different locations and compare them. Consequently, an important task of Voyager 2 is to check the data collected by its twin probe for similarities and differences. Indeed, a lot of information from Voyager 1 should be confirmed in this way, for example, the density of particles in interstellar space. However, things get even more interesting, not to mention confusing, when we look at the ways in which the probe's measurements differ dramatically. To understand the Voyager discoveries properly, we first need to understand how the boundaries of the solar system are structured. Basically, there is a dynamic network of magnetic field lines around the Sun that is invisible to the naked eye. These, in turn, act as paths along which electrically charged particles are shot into space, the so-called solar wind. While the solar wind spreads throughout the solar system, it eventually reaches the interstellar medium. But just like oil and water, the solar wind and the interstellar medium do not mix perfectly. As a result, the solar wind forms a bubble in the interstellar medium called the heliosphere. Thanks to the Voyager data, we know that it extends about 18 billion kilometers from the Sun into space. At the outermost edge of this region, the heliopause, interstellar space finally begins. Before Voyager 1 entered the threshold of the solar system, practically nothing was known about this area. However, the findings that the probe sent to Earth in this regard immediately left researchers in a state of both amazement and confusion, because many of their predictions had simply been wrong. For example, the interstellar magnetic field is in fact almost 3 times stronger than previously assumed, which means nothing less than that the interstellar particles also exert about 10 times more pressure on the heliosphere than written in the theoretical models. As groundbreaking and novel as the Voyager 1 data may have been, they were also accompanied by a major drawback: they were incomplete. This was for the simple reason that the instrument for measuring plasma temperature had been defective since the 1980s. However, since the counterpart on board Voyager 2 was still working, the researchers were all the more excited to see what information the probe would collect as it approached the heliopause. Today, we know that the plasma around the probe increased its density while at the same time slowing down and heating up. Beyond the heliopause, the interstellar medium reaches temperatures of almost 30,000 degrees Celsius, which is significantly hotter than scientists had predicted. However, since the plasma has an extremely diffuse and thin consistency, the temperatures around the space probes are surprisingly low. Furthermore, Voyager 2 found that the plasma crosses over from interstellar space into the heliopause, and in the opposite direction. When Voyager 1 crossed the heliopause, it encountered compact extensions of interstellar particles there. Strangely, its sister probe was confronted with a kind of particle stream that extends more than 150 million kilometers into the heliopause. No less strange is the fact that Voyager 1, about 1.3 billion kilometers before the heliopause, entered an area in which the solar wind slowed down noticeably. All in all, however, these strange differences reflect only a fraction of the mysteries that still need to be solved in the future regarding the edge regions of the solar system. For example, we don't even know exactly what shape the heliopause has, but at least we now know that the heliopause is surprisingly wrinkled. After researchers at Princeton University had registered an immense increase in solar wind pressure of almost 50% within a few months, they used the data to reconstruct the shape of the heliosphere and the heliopause, with the astounding result that the heliopause has gigantic folds that extend tens of astronomical units into space. Just to recap, the length of 1 astronomical unit corresponds to the mean distance between the Sun and the Earth, which is around 150 million kilometers. So, we are talking about folds that are several billion kilometers in size. No amount of Botox will help here. Perhaps, however, the information that the experts have been able to gather about the background to the wrinkle structures will help us. These result in detail from the high-energy particles that flow back in waves from the heliopause and collide with the solar plasma. Consequently, we are enriched with the knowledge that the heliosphere is by no means a static and unchanging entity, but rather a dynamic one that constantly billows, dips, and unfolds again. Indeed, the cosmic folds are even racing after the Voyager probes, because as soon as the solar plasma smooths the fold structures again, they continue to expand. Despite the advanced age of the probes, Voyager 1 and 2 will be spared the folds in their neck because they are simply flying too fast to be caught by them and thus be transported back into the inflating heliosphere. Yet the chase of the folds means that the distance of the probes to the heliosphere is not growing quite as fast as one might initially assume. And we would be delighted if the distance between your finger and the subscribe button now shrinks much faster than you would initially expect. Feel free to click the thumbs up and subscribe so you never miss a new video from us again. We'll see you soon.